Hello, my name is Rubén, and in this video, I will present you the main ideas and outcomes of the INESC-ID contribution to the Compare 2021 COVID-19 CAF Challenge. We relies on the use of transfer learning to develop deep representations of CAFs. So this challenge provides us with a common testbed to explore the possibility of using CAF recordings to automatically detect COVID-19. This question has been addressed by previous work, which point out to specific signatures of COVID-19 in speech, breathing, and cough. However, results are still not conclusive for a number of reasons. Probably one of the main limitations is the scarcity of properly annotated data. And that is the case here, where a relatively small quantity of data was available in the provided dataset to train our system. So we decided here to explore the possibility of using transfer learning to develop a set of 3 expert systems based on deep CAF representations, namely extractor embeddings, CNN embeddings, and problem-agnostic speech encoder features. After that, individual decisions are fed to a fusion system. The COVID-19 CAF dataset provided for this sub-challenge was used to train the individual classifiers and also to assess the whole system, while the COVID dataset by EPFL was used to train or fine-tune the deep representation extractors. We saw here the results of the baselines and the proposed systems. All the results are presented in terms of the unweighted average recall. If we look at the results of the development subset here, we can see that our proposals are competitive with or even outperform the baseline systems. And these results also show the potentials of the approach proposed here to overcome the scarcity of COVID-19 specific data. Our best result on the development subset was obtained by the CNEM-based system, but it did not generalize well to the test subset. Overall, our best results were obtained by the calibrated fusion of the 3 best individual experts, with an unweighted average recall of 72.3 and 69.3 on the development and test subsets, respectively. Finally, although the results are promising, we must be very cautious with the interpretation of these results. Further analysis of the results and the proposed system will be provided in a following video. Thank you very much for your attention. Hello again, I'm Rubén, and in this follow-up video, I will present some more details of our work on COVID-19 detection from CAFs. Let me begin by the architecture of the proposed system, and in particular, by the deep CAF representation structures at the basis of the 3 expert subsystems. So, after preliminary preprocessing, deep representations are computed from raw CAFs or basic audio features. Expector embeddings have been used for the detection of sleep apnea, Parkinson's disease, Alzheimer's disease, and depression, among others. Similarly, our hypothesis here is that extractor-like embeddings trained with CAF recordings might convey relevant information for the detection of COVID-19. Here, we implemented a reduced version of the factorized time delay neural network by Villalba and colleagues. This table shows the architecture that was trained in a 2-step multitask setting using the CAF cortex. And 5-level embeddings are extracted from the last layer. CNN embeddings have been used for COVID-19 detection, but not always particularly adapted to this specific problem. So here we implement a simplified version of the VGG's model by Hershey. This table shows the architecture where layers 1 to 7 correspond to those of the original model with pre-trained weights, and segment-level embeddings are computed at layer 8. We use this model in 2 settings, either as pre-trained generic feature extractor or fine-tuned using COVID data, for which layers 9 and 10 were included. Finally, problem-agnostic speech encoder features are supervised representations provided by Romanelli and colleagues. The model architecture consists of an encoder followed by a battery of regressors and classifiers, node workers, that are jointly trained to obtain robust, general-purpose, and transferable representations. The model was trained from scratch using the libre speech or COVID datasets to obtain generic or COVID-19 specific features, respectively. Then, support vector matching classifiers were trained on top of these rich representations to detect COVID-19. And finally, system-dependent weights and offsets were determined through linear logistic regression to combine the decisions of the three experts. Now, I will briefly talk about the corpora. This table shows the number of samples in the COVID-19 corpus relays for this challenge. And after inspection, we found some recordings with a narrow bandwidth of 4 kHz. The problem is that all the narrowband files in the train and development subset correspond to COVID-19 positive examples, which might bias the systems trained using this data. So to further analyze this, we decided to create a second version of this dataset, denoted as full band, by removing all the narrowband files in the train and development subset. Both versions were used to independently train and optimize the COVID-19 classifiers, while just the original test subset was used for the final assessment. Secondly, the COVID corpus by EPFL was used to train and fine-tune the deep cough representation extractors. This is a much larger dataset from which we use the cough recordings with associated self-report age, gender, and COVID-19 status labels. Also, a smaller portion of the dataset, and originally annotated by experts for a number of conditions and diagnosis, was used to train the egg vector embedding instructor. So let me come back to the experimental results. Some of them already presented in this previous video. And now I want to focus on the results on the original and the full band development subsets. And we can see a remarkable lower performance for the latter. The only exception is in the page-based system, which shows more robust results. So these results seem to confirm our suspicion on the possible bias introduced by the positive narrowband files in the train and development subsets of the released dataset. To conclude, we must be very cautious with the interpretation of the results of this and other works on COVID-19 detection from speech and respiratory sounds, given the severe implications of this disease. There are a number of factors that must be considered carefully, such as the quantity and quality of the data, the fact of using self-report COVID-19 status in many cases, and the shared spurious effects and others. Finally, results are promising, but still not enough for a practical screening of COVID-19 in real-life conditions. And larger and more controlled data sets are definitely needed for this. And that's all. Thank you very much for your attention.
Okay, thank you. Well, I forgot to mention, I guess you can ask questions in the second button to the right with the question mark. You can write your question. I don't know whether the audience can ask questions. Yeah. Okay. Hi, Rubén. How did you calibrate the scores? That's your question.
Yeah, so using the development data, we train a register system to combine all the three soft outputs from the three individual subsystems in our work to calibrate, to fuse the outputs from the individuals to get the final decision function.
Okay, thank you.